Welcome back to the Deep Dive. Our goal, as always, is to take complex topics, break them down, and give you the core insights. Today, we're diving into something really fascinating, the interface between biology and machines, specifically brain-machine interfaces, or BMIs. Now, when you think about linking a brain to a computer, you almost certainly picture electrical signals, right? We've gotten pretty good at reading those bioelectrical potentials, the fast sort of digital pulses the brain uses. But our sources today argue that this might be a fundamental misunderstanding of how consciousness, well, speaks. That electrical readout might only be half the story.
That's a perfect way to put it. It's like we've been listening to the brain's telegraph signals, quick clicks and tags, but completely missing its poetry, the richer language. The mismatch is this. Electrical signals are great for speed, for immediate actions, but so much neurological information, the really deep stuff like memory, mood, emotion, that's largely communicated chemically through neurotransmitter.
Okay.
So if your BMI is only listening for electricity, it's essentially deaf to this whole chemical dimension of your inner world.
Which means we're really just scratching the surface.
Yeah.
Only accessing the shallow end of the neural pool, so to speak.
Yeah.
So our mission today is to explore a brand new technology trying to bridge that exact gap. It's described as the first successful chemically mediated artificial neuron.
Right. And the goal here isn't necessarily to replace the electrical BMIs we have. It's more about complementing them, giving us a way to finally access and interact with those chemical signals in the central nervous system. And to demonstrate this, the researchers focused on a really key chemical messenger, dopamine, DA.
Dopamine, okay, the motivation molecule.
Exactly. It's central to reward learning reinforcement. So if you can build an interface that truly communicates using dopamine, you're tapping into some very fundamental brain mechanisms.
Right, so let's start with the basics. If you want to build a device that can have a real chemical conversation with a biological neuron, synapse to synapse, what does it absolutely have to be able to do?
It really boils down to three essential functions, mirroring what happens at a natural synapse. First, it needs robust neurotransmitter recognition. It has to, receive that chemical signal, understand it, and usually translate it into something the machine can process, typically an electrical signal.
Okay, receive the message.
Second, it needs synaptic plasticity. This is the ability to adapt, to change its response based on past signals. Essentially, it needs to learn. It needs memory.
Processing and learning, got it. And the third piece?
The third is it has to talk back. It needs a mechanism for releasing neurotransmitters itself on command, mimicking how a neuron fires off its own chemical signals.
And that last part, the talking back chemically, that's been the real hurdle, hasn't it?
Absolutely. Our sources point out that many existing neuromorphic devices, things like phase-change neurons or artificial nerves, they respond to electrical inputs, or maybe physical things like pressure or light. But they generally lack both the specific chemical sensing and the chemical releasing needed for a complete two-way chemical loop. That's been the missing link.
Okay, so to make this full chemical dialogue happen, these researchers basically had to engineer three distinct blocks, working together in sequence into one integrated system. Okay, let's unpack this, starting with the first building block.
Let's do it. Block one is the dopamine electrochemical sensor. Think of it as the system's nose. Its sole job is recognition. Detect DA molecules and convert that chemical presence into an electrical current.
Now, sensors in biological environments.
Yeah.
That sounds tricky. There's so much chemical noise. How do they make sure it was only listening for dopamine?
That's a critical point, and it comes down to some clever material science. They used a carbon electrode, but modified it with a composite material, specifically carbon nanotubes, CNT, and graphene oxide.
Graphene oxide.
Yeah, and the GEO is the key here. It has a strong negative charge. Dopamine molecules are positively charged. So the GEO surface basically acts like a magnet for DA.
Contracts the target.
Exactly. And crucially, it repels common interfering molecules in biofluids like ascorbic acid, which tend to be negatively charged, so it filters out the noise.
Ah, very smart. So it's not just detecting something, it's specifically locking onto dopamine with high selectivity.
Precisely. And they showed it works across a range, from about 1 micromolar up to 1.5 millimolar, which nicely covers the typical concentrations you'd find in a real synaptic cleft.
Okay, so block one confirms the DA signal and turns it into electrical current. What happens to that current next?
That current feeds directly into block two, the memristor device. This is where the processing and, importantly, the plasticity, the learning happens.
Decision maker, you could say.
Yeah.
What's this memristor made of? Anything special?
It's a fairly standard crossbar structure electrically, but the material in the crossbar is quite unique. They used silk fibron.
Silk, like from silkworms.
Yep, exactly. And that choice is really important for potential future applications inside the body. Silk fibrin is known for being incredibly biocompatible and also mechanically flexible. Embedded within the silk matrix are tiny silver nanoparticles. And it's the way these nanoparticles connect or disconnect, changing the resistance, that forms the basis of the memory.
Okay, plasticity. This is a core concept. How does this artificial synapse, this memristor, actually show it's remembering something rather than just reacting instantly?
Think about it like pathways. If the memristor gets a weak electrical signal, maybe from a brief low concentration of dopamine, the resistance changes a little bit, temporarily. That's like short-term plasticity, STP. The change doesn't stick. The resistance snaps back to its default high state, the high resistance state, HRS. No lasting memory form.
Like a footprint in sand, easily washed away.
Good analogy. But if you hit it with a strong signal, a big pulse of current, or, and this is key, if you give it repeated weaker signals over time.
Oh, accumulation.
Yes, then you get long-term plasticity, LTP. Stable conductive pathways, filaments, formed between those silver nanoparticles within the silk. The device switches to a low-resistance state, LRS, and the state is non-volatile, it sticks around. They showed it could be maintained for, well, over 10,000 seconds, so hours. That LRS is the memory. It's learned the connection.
Here's where it gets really interesting, connecting that memory state back to the function. Okay, so we have recognition in block 1, processing and memory in block 2. Now block 3, the release mechanism, a heat-responsive hydrogel.
Right. This is the output stage, acting like the little vesicles in a nerve terminal that hold neurotransmitters. They essentially made tiny pouches using a temperature-sensitive polymer, specifically polyvinyl alcohol, or PVA hydrogel. And inside these pouches, they encapsulated dopamine.
So the dopamine is preloaded, waiting for a signal.
Exactly. And the signal comes directly from the memristor state, if and only if the memristor transitions into that learned low-resistance state, LRS.
The memory state.
It completes a circuit that activates a tiny integrated heater.
Okay, so LRS turns on the heat. And the heat.
The heat causes the PVA hydrogel network to temporarily loosen up, kind of dissociate, releasing the trapped dopamine.
Yeah.
And critically, they engineered this release to happen in a very narrow body-safe temperature window, between 37.5 and 43.5 degrees Celsius, just above normal body temp, so no risk of burns.
Wow. So it's a physical release triggered by an electrical state change that was originally triggered by a chemical input. That's the full loop.
That's the entire sequence. Chemical in, electrical processing with memory, chemical out.
Okay, let's zoom out and look at this integrated system in action. DA hits the sensor, current memristor, maybe changes state, LRS, might trigger heat, GA gets released. This is where that in-sensing memory concept really comes alive.
Absolutely. They demonstrated this beautifully. If they applied a tiny bit of DA, say 10 micromolar, the sensor sees it, but it's not enough to flip the memristor into the long-term memory state, the LRS. Nothing really happens downstream.
Too weak.
Right. If they blasted it with a high concentration, like 200 micromolar, boom, instant switch to LRS.
Yeah.
Non-volatile memory formed immediately.
Makes sense. But the really biological part is that buildup, right? The weak signals adding up.
Exactly. They show that even if you just give it a series of small successive nudges, gradually increasing the DA concentration up to just 20 micromolar, it still eventually forms that strong connection and flips into the LRS. It integrates the weak signals over time. That's very much like how biological neurons strengthen pathways through repeated use, like learning a habit.
Okay, now this is the crucial connection I wanted to get to. Once that connection is learned, once the memristor is already sitting in that low-resistance state from a previous strong or repeated signal, how does that stored memory change how the system responds next time?
It changes the threshold dramatically. So if the system hasn't learned yet, it's in the high-resistance state and needs a relatively strong DA signal, 20 micromolar or more, to get enough current to trigger the heater and release its own DA.
Okay, the initial learning requires a decent push.
But once it is in that learned LRS state, the resistance is already low. So now it takes much less input to trigger the release. The threshold concentration drops significantly. They showed it only needs a DA concentration above 5 micromolar to trigger the release.
Wow, wait, from 20 micromolar down to just over 5, that's a 4-fold increase in sensitivity, effectively.
Yeah, it's a huge difference.
So once the artificial neuron has learned or practiced that connection, it becomes much easier to activate. It responds to a much quieter chemical signal. That feels very biological. that pathway is now reinforced.
That's exactly the point. The memory state directly controls the ease of future communication.
Okay, so the system works beautifully on its own. But the real test is, can it talk to actual biological cells?
Yeah.
They use PC12 cells, which are a common model for this kind of work, right?
Yes, PC12 cells are often used because they release neurotransmitters like dopamine. This was the test of interneuron mimicry. Could it have a two-way chat? First, receiving, they stimulated the real PC12 cells using potassium ions, which makes them release their own dopamine.
Okay.
And the artificial sensor on the device successfully detected that naturally released DA. Check one. It can receive the biological chemical signal.
Good start. Now, could it send a message back? Did its DA release do anything to the cells?
It did. They then triggered the artificial neuron, gave it a strong DA input to switch the memristor and activate the heater, causing it to release its stored DA. And that artificially released DA successfully activated the nearby PC12 cells. They could measure this activation by seeing a rise in calcium levels inside the cells and also changes in their potassium currents.
So it closed the loop. Chemical message sent by the machine, received and understood by the biological cell. That's pretty remarkable.
It's the first demonstration of that complete chemical neuromorphic loop.
Incredible.
Yeah.
And they didn't stop there. They pushed it towards actual function, demonstrating motor neuron mimicry, using this chemical signal to cause movement.
Right. The first demo was quite visual. They gave the artificial neuron a strong DA stimulus, it went through its process, released its DA, and that signal was used to activate a robotic hand, making it perform a handshake. So chemical input leads to mechanical action via the artificial neuron.
Okay, cool robot demo. But the more compelling part, biologically, was connecting it to actual nerve tissue, right? A mouse sciatic nerve.
Exactly. Because the sciatic nerve controls leg movement, it provides real biological motor feedback. This wasn't just on-off. They wanted to see if they could get nuanced control.
And could they?
Yes. This is a really key result. They gradually increased the dopamine concentration, stimulating the artificial neuron step by step from maybe 25 up to 60 micromolar. And as they increased that chemical input signal, they observed the mouse leg connected to the sciatic nerve move through a progressively larger angle.
Oh, wow.
It went from basically 0 degrees up to about 8 degrees plus or minus. So it wasn't just move, don't move. It was showing that the amount of chemical signal dictated the degree of motor response.
A graded response. That implies information is being encoded in the concentration chemically and translated faithfully into a proportional physical output through this artificial bridge.
Precisely. It demonstrates analog control, chemically mediated across the artificial synapse to a biological nerve.
Okay. This has been quite the deep dive. Let's try and summarize. We've seen the development of what's arguably the first chemically mediated artificial neuron. It can handle the whole process. Recognizing a specific neurotransmitter, dopamine, processing that signal with memory-like plasticity, and then releasing its own neurotransmitter in response. Bidirectional chemical communication.
It really lays the conceptual foundation for true chemical BMIs. It proves we can go beyond just eavesdropping on electrical activity and actually engage in that chemical dialogue the brain uses for so much complex function, the potential implications for neuroprosthetics that feel more natural, for treating neurological conditions chemically, for advanced human-machine teaming. They're really significant.
Of course, we should be clear, the sources themselves point out this is still early days. It's a proof of concept. There's engineering work needed, right?
Oh, absolutely. They need to improve the speed, get the power consumption way down, figure out how to package this reliably and stably for long-term use, potentially inside the body. Lots of practical hurdles remain.
Standard path for new tech.
But the fundamental breakthrough, bridging that chemical communication gap, that's been achieved here.
And that brings us right back to where we started, and maybe the most interesting thought to leave you with today. We saw very clearly in this artificial system how memory, the plasticity, the LRS state, directly changed the communication threshold, made it much easier to talk once a connection was learned. Is so much of our consciousness, our memories, our emotions are governed by similar, subtle chemical thresholds and pathways strengthened over time. What happens when BMIs can finally interact with that? What level of nuanced understanding, control, maybe even empathy could we build into neuroprosthetics or future cyborg systems once we move beyond purely electrical interpretations and truly start speaking the brain's chemical language? Something to think about.